electron-rich entities can approach a carbonyl systems, which are electron deficient species. So we can again revert the reactivity. If we are having a nucleophile, which is carbon nucleophile, let's say you have come across enolates. Now we have changed the substrate. The substrate becomes electron-rich rather electron deficient. So that can be added to any carbonyl type systems or can react with any entity electrophilic center rather reacting with a nucleophile. So these are the four type of additions you have come across already. And in this case, we are just going through the other type of the reactions, which are substitution reactions in fact. So substitution reactions are very obvious that in a substrate you are having some atom, maybe hydrogen, maybe some other group or a group of atoms. So if these are being replaced by someone, this is simply called a substitution reaction. So a substitution reaction is in fact a replacement reaction, meaning we are replacing an atom or a group of atom in a substrate by something else. This is called substitution reaction. So let's see, start the substitution can be further classified into four categories. One is if we are having a sp3 hybridized carbon, just like you are most likely familiar with. If we are having a sp3 hybridized carbon and a group is attached with this, which is normally electron withdrawing group. So X group is an electron withdrawing group. If we are reacting it with a nucleophile, so because this is a electron ring, this X group is something which is having high electronegativity. So as a result, it is withdrawing electronic density, making this sp3 hybridized carbon electron deficient. So if it is electron deficient, so definitely the nucleophile can only approach rather a electrophile. So electron rich, electron deficient entity. You have seen this in your already curriculum in previous classes. So nucleophile approaching an electron deficient center, electron rich, electron deficient entity. But the carbon is sp3 hybridized. The same we can revert in fact. How? Let's see. If we have a carbon keto form in tartameric form to its enol form reacts with the base to form enolate. Enolate this carbon, let's say, just focus on this alpha carbon, not the beta carbon. This alpha carbon is no electron rich. It is no sp2 hybridized, but if it reacts with electrophile, it shall convert into sp3 hybridized. You see, one alkyl group, one hydrogen is already present. If an electrophile is reacted with this, it shall become asymmetric center. Mean this carbon sp2 hybridized shall be converted into sp3 hybridized carbon in fact. So this is the totally opposite to this one. Here a carbon is electron deficient, that's why reacting with a nucleophile. The same type of molecules we have converted a carbon into electron rich entity, rather electron deficient. So that's why it is not going to react with the nucleophile. Two electron rich or two electron deficient entities cannot react with each other. So therefore, this carbon, look at this alpha carbon, it shall prefer to react with an electrophile. So this is the change in reactivity you shall also come across. We shall study this in very much detail in some by name reactions. You shall come across Perkin reaction, you shall come across a variety of different reactions involving this type of protocols. But this is very familiar to you. A sp3 hybridized carbon reacting with a nucleophile can undergo SN2 mechanism, SN1 mechanism, SNI mechanism. This is what you have already come across in earlier classes. But we shall focus on SN1 prime, SN2 prime, SNI prime, and tetrahedral mechanism in this due course. So that are additional to you. So what are SN1, SN2, SNI, SN1 prime, SN2 prime, SNI prime, and similarly tetrahedral mechanism. Another additionally you shall see enzymatic assistance, which is also called neighboring group participation. So these are a few things which are additional what you have already come across. So your knowledge of previous aliphatic substitution shall be further strengthened. So these are the two aspects. One is the substitution taking place on sp3 hybridized carbon atom. Second, if it is the substitution is taking place on sp2 hybridized carbon. Now here, just look at one thing, what very important aspect you have seen. This carbon, where this bond is making, there was a hydrogen in keto form, alpha carbon. This hydrogen moves to keto form, enol form. Enol will react with the base to generate enolate. So you see what is the overall reaction? This hydrogen is replaced by electrophile. So it means this carbon is acting as a nucleophile. So enolate is a core. So here substitution is taking place. This hydrogen is replaced by electrophile. So very similar here. Here this group is replaced by a nucleophile. Here it is electrophile is used because our substrate is electron rich. Here it is a nucleophile is used because this carbon center is electron deficient due to connectivity with the high electronegative atom, which is X. So this is one type of the substitution taking place on sp3 hybridized carbon. In fact, both of these two. Hydrogen replaced by electrophile, more electron withdrawing group replaced by a nucleophile. This is what is going on, the major difference between the two kind of substitution. Because this group, if we have all carbon present in a molecule or sp3 hybridized, it is called aliphatic group. If we are having a one double bond present, that is normally called olefinic. If triple bond, that is called an alkynic. And if it is conjugated, more than one double bonds are present, this is called aromatic system. So we can have a sp3 hybridized carbon, sp2 hybridized, or sp hybridized carbon even. So if we are observing, this is something sp3 hybridized carbon, we have a group, so it can be replaced two ways. It can be reacted with nucleophile. The same carbon can be reacted if there is a carbonyl carbon or a nitro group, etc., is present next to that carbon where substitution is taking place. So it is making, due to enol formation, it is making this carbon electron rich rather electron deficient. That's why electrophile. This is called aliphatic system. Aliphatic nucleophilic substitution, which is also read as substitution nucleophilic. So substitution nucleophilic also takes place to the aromatic substrate. So we are going to differentiate this aliphatic SN2 reaction, SN1 reaction, which are also taking place to the aromatic system, but mechanism is entirely different. So this is aliphatic nucleophilic substitution reaction. This is aliphatic electrophilic substitution reaction. Both are not same. Both are different. Here nucleophile is used, here electrophile is being used. Right, so switching over to the other category, which is here, if we have a sp2 hybridized carbon, one of the hydrogen is replaced by electrophile. This is the change. Right, one of the hydrogen is replaced by electrophile. So you shall see the mechanism of this in much detail. But if let's say our substrate is electron rich, that's why reacting with an electrophile. But let's say due to some reason we make this group or this system electron deficient. Let's say I have attached a electron withdrawing group minus R group to meta or para ortho or para position of this. If we have this group, you remember it is electron withdrawing shall generate electron deficiency at ortho and para. So by resonance, you shall have a positive charge here, positive charge here, and a positive charge here. So this carbon where X is bonded, it is getting positive charge, full positive charge. So it means this is electron deficient. So a nucleophile would be able to approach this system. So here we observe the X normally, which is halogen or maybe triflate, etc. That is being replaced by a nucleophile. So aromatic system, but reacting with nucleophile. So this is electron deficient. In fact, that's why reacting with a nucleophile. So again, here we shall have four different classes of substitution reactions. Now we are going to start first with the if our substrate is electron rich, aromatic, and undergoing electrophilic substitution. We shall also come across nucleophilic, electrophilic, nucleophilic aromatic substitution or aromatic nucleophilic substitution. This is aliphatic nucleophilic substitution. Both are different. They are not same. So anyhow, our first focus is these type of entities, the mechanisms involve this type of substitutions. Let's start with this. When we are talking about substitution aromatic mechanisms, so three mechanisms are involved during this. We are just talking about three type of mechanism of this category. Electron rich aromatic system reacting with an electrophile in which one of the hydrogen is replaced by electrophile. We are talking about this. It follows three mechanisms. One is called arrhenium-ion mechanism. Other is called SE1 mechanism. SE1 stands for substitution electrophile. One stands for kinetics, mean it is a first order mechanism. Third one is called simultaneous attack and departure mechanism. So these are the three mechanisms that you shall come across in aromatic substitution reactions. Aromatic electrophilic substitution we are talking about at the moment. Let's start with first arrhenium ion mechanism. What is arrhenium ion? Arrhenium ion is derived from a word arene, A-R-E-N-E. Arene means what? Arene means that aromatic system, aryl group that we commonly call. So A-R-Y-L. Arene is the word which you use for all aromatic systems. This is benzene, this is naphthalene, this is anthracene, phenanthrene, not only carbocycle but heterocycles as well, just like pyrrole, indole, and all other heterocyclic systems. All of these are collectively called arenes by IUPAC nomenclature. Aryl group and alkyl. Alkyl is derived from alkane. Alkenyl. Alkenyl means this is a double bond containing alkyl group, and alkynyl, one triple bond containing alkyl group. So these are the terms that we are very frequently using. So you should be remembering this, what means by this. Arrhenium ion. Keeping in mind whenever we are talking about arrhenium means it is derived from aromatic system, just like ammonium, if you remember. Oxonium mean they are positively charged. So here we are using arrhenium ion mechanism. So you shall see what is arrhenium ion. First of all, I have drawn this mechanism with a very simple illustration. Let's say you are familiar with benzene ring system. So I have taken this as an example. It is reacting with an electrophile. Our benzene ring system has 6 pi electron. You remember, this is highly electron rich system. So this electron rich system reacting with the electron deficient entity. So what shall happen in benzene case? All carbon positions are identical. Keeping in mind, it doesn't mean this carbon and electrophile are bonding. So why not bonding here? Why not bonding here? It can bind anywhere because all 6 positions in benzene are identical. All right. So what happens? This 1 pi electronic density transfers towards electrophile. So we are getting hydrogen is already present on this carbon, hydrogen is already present on this carbon. So both of these hydrogens are present here. So electrophile, this carbon to one carbon, electrophile is bonding, the same is bonding with another hydrogen. So this carbon is bonding with a hydrogen only, 3 atoms. So that's why it is carrying a positive charge, electron deficient. So a carbocation is generated. Keeping in mind, this is called carbocation, not carbonium ion. You shall see that in aliphatic mechanisms in much detail in SN1 especially. So anyhow, we shall introduce you a classical carbocation and a non-classical carbocation, etc. But in just upcoming lectures, you shall find that one. So in this case, you can observe this is in fact a positive charge, mean electron deficient center at this position. So this is the very first step, is a slow rated step. All right, this is the first step, is always slow rated, and I have presented this in parentheses. This is in fact intermediate. It is highly unstable. Sorry, not highly unstable. This is quite stable one, because this positive charge is resonance stabilized by these pi electrons. This double bond can donate electron pair here to generate a positive charge here. Sorry, double bond here and a positive charge here. This positive charge shall be stabilized by this. So it has 3 resonance forms possible. So due to these 3 resonance forms, this complex or this intermediate is quite stable one. Next step is in which this hydrogen leaves in the form of H positive, and it leaves the system. So we get a double bond here and we get this product. What is happening in this molecule? We are having a hydrogen here that is being replaced by electrophile. So this is an aromatic electrophilic substitution reaction. So all this is called arenium in which a benzene ring system or any other aromatic ring system, either carbocycle or heterocycle, reacts with an electron deficient additive that we call electrophile. It is always a slow rated step, result in the formation of this intermediate. This intermediate undergo in a fast rated mechanism loss of H positive ion to generate a product. Keeping in mind, this is C, a substrate and a reagent are reacting to form an intermediate, and in fast reaction, intermediate is going to form product. So reaction rate shall be dependent upon which step, the slow rated step, which is this one. In this, both reactants are reacting. So that's why it shall be second order kinetics, but it is stepwise mechanism. This is not a concerted mechanism.